Okay, now we're going to learn how to name ionic compounds. In order to name ionic compounds, we need to be able to name ions, just the individual parts that make up your ionic compound. Remember, your ionic compounds are made up of a cation and an anion. And the cations have a name and the anions have a name. Okay? Your cations can be made up of two types. They can be monoatomic. That just means a single element, something straight off the periodic table. For instance, like Ca2 plus, Ag plus. Those are monoatomic cations. You can also have a polyatomic cation. There's one that you need to know, and that is NH4 plus. So if a compound starts with a metal, something straight off the periodic table, a monoatomic cation, or NH4 plus, odds are it's an ionic compound. The other part of an ionic compound is the anion portion, and that can also be made up of monatomic and polyatomic. The monatomic is something straight off of the periodic table. It is a single element, like N3 minus, Cl minus, or it can be made up of a polyatomic. Polyatomics, there's a whole bunch of polyatomic anions, a whole bunch, and you've got that list up in school with you that you should download. And if you have access to a printer, print so that you have it in front of you because we will be using those for the rest of the school year. So when we're talking about cations and anions, we can read the charges off of the periodic table for the most part. There are a few little exceptions, and we're going to talk about those really briefly now and then more in depth in a minute or two. So for instance, your representative elements, you know the charges because you've labeled your periodic table, but you can also figure it out by what is the shortest path for an element to gain an octet. When you do that, you realize that everything in this first column can get a +1. Everything in the second column, your alkaline earth metal gets a +2. Over here, most of them get a +3. Here, you can be plus or -4, -3, -2, and -1. Most of them, not all of them, most of them. Okay, then you have your transition metals. Your transition metals have variable charges. They have variable charges. So what that means is that their charges can depend on the situation. So because of that, when we're naming our transition elements, we need to say in the name what the charge was of that element. For instance, iron can be a +2 or it can be a +3. So we need to say that in the name. There are three exceptions for the transition elements. There are three elements that you need to know that have a fixed charge. And these are the elements that we call ZAC: zinc, silver, and cadmium. These guys have fixed charges. In other words, their charges do not change. They are always the same. Zinc is always a +2. Silver is always a +1. Cadmium is always a +2. You must have that noted on your periodic table or written down because you must know those charges because those are we're little exceptions. Those guys, we do not need to denote their charge because the charge never changes. Okay, then there are these four over here. We call these the pass elements. It's lead, arsenic, tin, and antimony. These guys are not transition elements. However, they also have variable charges. So what that means is when we give the name of these guys, we must say what charge they might have in that situation. Okay? So just keep that in mind. So if I were you on your periodic table, you've already labeled your charges up here for your representative elements. I would write in the top right-hand corner of ZAC what their charges are: +2, +2, and +1. And I would outline those three just to draw your eye to it. And then I would also outline the pass elements, again, just to draw your eye to it. Okay, so when we're naming ions, we first have our monatomic ions. When we're naming them, um, we use the full name of the metal ion, and we just add the word calcium. So add the word ion to it. So for instance, if you just had calcium with no charge, you would call that calcium. If you just said Ca with no charge, you would call it calcium. But if you see Ca2 plus, got a charge, you have to call it calcium ion, those two words. If you have a monatomic anion, the way you name that is you're going to drop the ending of the name and you're going to replace the ending with IDE, like we did for the covalent compounds, IDE. Then we're going to add the word ion to the end. So for instance, if you had just Br by itself, it would be called bromine. But if you have a charge with it, it's bromide ion. The whole bromide and ion, those two words. Okay. Then you have your polyatomic ions. How do you name those? Well, you just look them up. Look them up on that list that is in Schoology. You look them up in that list and in Schoology. And you look up what, let's say, CO3 2 minuses. You look it up, you say, oh, that's carbonate. And that's how you name it. You just look it up. Okay? So let's name some ions. This guy is sodium with a +1 charge. So it's a monatomic cation. So we call this sodium ion. This one is a monoatomic ion with a plus charge. So we call it calcium ion. This one is a monatomic cation with a +3 charge. So we call it aluminum ion. If it was just Al, no charge, it would be called aluminum, but now it's called aluminum ion. P3 minus. This is a phosphorus with a -3 charge. So we call it phosphide ion. We replace the ending with IDE, phosphide ion. This guy is oxide ion. This is radium ion, bromide ion. Okay, now for those pass elements, the transition metals and those pass elements, they need Roman numerals to denote their charge, with the exception of zinc, silver, and cadmium, which are transition metals that do not need Roman numerals because they have fixed charges. So you're going to have to know your Roman numerals for this class. 1 through 10 ideally, but here's 1 through 5. 1 is I, 2 is II, 3 is III, 4 is IV, 5 is V. So we need to know, keep that in mind. So how do we name that? So for instance, iron can have a charge of +2 or iron can have a charge of +3. The way we distinguish between the two is that we say this is iron 2 ion. This 2 denotes its charge. That 2 says that this iron that we're talking about has a charge of +2. It's a metal, therefore it's going to be a cation. Remember, your cations are metals. Your metals are cations. All right. This one is an iron, but it has a charge of +3. So its name is iron 3 ion. Okay, so let's practice. Name these ions. We know this is calcium ion, sodium ion. This one is iron, got a charge of +2. We call it iron 2 ion because it's a transition metal. This one, SN4+, it is not a transition metal, but it's one of those pass elements, those 4 non-transition elements that have variable charges. So we need to say that charge in the name. So this guy is called tin 4 ion. Zinc. Zinc is a transition metal, but it's one of the ZAC elements, the ones that don't have fixed charge. So we don't have to denote its charge in its name. So that is zinc ion by itself. Okay. Why don't you pause the video right now and see if you can name these 4 ions. And then I will discuss them in a minute. Okay, welcome back. Pb4+. This is one of those pass elements, so we're going to have to denote its charge in its name. This is lead 4 ion. This is a transition metal, and it's not one of the weird exceptions, so we also have to give its charge. That is chromium 2 ion. This is a monoatomic cation, one of the representative elements. So that is just lithium ion. So, first, in summary, you have the elements that need Roman numerals are the transition metals and your pass elements. The elements that don't need Roman numerals, the transition metals that don't need Roman numerals are ZAC, your zinc, your silver, and your cadmium. Okay, your polyatomics. We can have polyatomics that are cations and we have polyatomics that are anions. There is only one polyatomic that is a cation, but before we talk about that, let's talk about what a polyatomic ion is. It's a group of mostly covalently bonded atoms that have an overall charge. In other words, a bunch of nonmetals that have been bonded covalently, held together covalently, but overall they picked up an electron or got rid of an electron somewhere in order to achieve octets in their bonds. So because they have an overall charge, they can be involved in ionic compound. And they behave as a unit. They behave as a group. We don't break up that group. They stay together. They stay together. Your only polyatomic cation is NH4 plus, ammonium ion. You need to know that one. Your polyatomic anions is a covalently bonded group of atoms that have a negative charge and they stay together. They're easy to deal with in naming and formula writing if you think of them as one unit. Don't break them up. You don't alter them at all. You treat them as one unit. The way I like to always think of them is I always put parentheses around them with the charge on the outside. That way it keeps it as one unit. To name these guys, you just look it up in that chart. So you look at your polyatomic ion sheet in school and you name these. So if I were to give you all these, you would go look up CO3, 2 minus on your polyatomic ion sheet, and you would see that is called carbonate. OH minus. OH minus is a polyatomic. It is called hydroxide. It is one of the few polyatomics that end in IDE. Most polyatomics end in ATE or ITE. ATE or IT8 or IT. Okay, this guy, you look it up, it is nitrate. This guy you look up, it is sulfate. And the last one that you look up, it is phosphate. And you just look them up and write down their names. These are called carbonate ion, hydroxide ion, nitrate ion, sulfate ion, and phosphate. There's a phosphate ion. There's a bunch of these that you just need to know or be able to look up and identify them. They're treated as one unit. Okay, so now we've talked about naming our cations and our anions separately. But what we're trying to learn how to do is name compounds, where those cations and their anions are together. So we're going to start talking about naming binary ionic compounds. So on your flow chart, this is what we're looking at. We've blocked out everything else for now. We've already done a little portion of it, but we're blocking everything else for now. And we're going to be naming binary ionic compounds. So what we're going to do is we're going to ask ourselves when we're running through naming, we're going to ask ourselves, is there a metal in the compound? Or is there ammonium, NH4 plus, in the compound? If there is, you're going to ask, is that metal a transition metal? Or is ammonium a transition metal? The answer is no. We're going to count the different number of elements. If it's ionic binary, we name the metal or the polyatomic first. And we name the non-metal second and change the ending to "ide." This is what we're going to be doing. We're going to run through it step by step. So to name binary ionic compounds, remember your ionic compounds are made up of a cation and an anion pair. And you know how to name the ions separately. So just to name the compound, you just put those separate names together. And if there's Roman numerals in the ions names, then you don't forget that and you add that to the name. And again, cations are always written first. Cations are always written first. In chemistry and in life, we always lead with the positive. Cations go first, they're positive. We lead with the positive. To remind you what that looks like, there's an ionic compound. It is a transfer of electrons. Chlorine has 7 valence electrons. Sodium has 1. Sodium transfers its electron to chlorine. When it does that, it gets a positive charge. Chlorine gets a negative charge, and then they are held together by an electrostatic charge. Your overall molecule is neutral because you have a positive and a negative, and that balances out. It is neutral. Okay, so let's try some naming. You have aluminum and you have a nitrogen. So if you were to look for the ions here, aluminum is the cation. It is an Al3 plus. Nitrogen is the anion. It is an N3 minus. If you were to name this, name each individual ion, this would be called aluminum ion. This would be called nitrite ion. To put the compound name together, you just put these two names together and drop the word ion. That becomes aluminum nitride. Okay, let's try the same thing for sodium. For Na2O. The anion here is Na plus. The cation here is Na plus. The anion is O2 minus. You read that off the periodic table. Sodium ion is Na plus. This guy's called oxide ion. To put them together, you get sodium oxide. If you were to use your flow chart, to name this, you would say, let's do the Na2O. You would say, is there a metal in the compound? So you should be following along on your flow chart. Is there a metal in the compound is the first question. Yes, there is. This is the metal right here. The next question says, is that metal a transition metal or is it one of those pass elements? The answer is no. So we're going to go to the left. Then we're going to count the different number of elements. How many elements do we have? Sodium and oxygen. That's 2 elements. So this is ionic binary. The flowchart says that the way to name this is you name the metal first, sodium, then you may name the non-metal second and change the ending to "ide," sodium oxide. Okay, so now let's look at this next one, FeO. Okay, we're going to use our flowchart. Is there a metal? Yes, it's iron. Is that metal a transition metal? Yes, it is. This guy's called oxide, by the way. We need to find out what charge iron had here. How are we going to do that? We're going to use the anion to help us. Remember, our compound needs to be electrically neutral. It needs to be electrically neutral. It means the negative side must equal the positive side. Well, if the negative side is -2 and we only have one iron, then the positive side must be a +2. So that means you have an Fe2 plus. What is that guy called? Iron 2 ion. So now if we were to name this, we would name it iron 2 oxide. Okay, now let's do the same thing for the one below it, Fe2O3. Again, our anion is O2 minus. Oxygen always is a 2 minus. It doesn't ever become anything else. So if we were to name this, we need to find out what the charge is for iron. Okay, so what does that look like? Well, we have 2 irons and we have 1, 2, 3 oxygens. We're going to add -2, -2, -2 because oxygen always has a charge of -2. We have 3 of them. So our cation side is a -6. That means our anion side is a -6. Our cation side must be a +6. Well, we have 2 irons contributing to that +6. That means each one must be a +3. That means the iron we had before has to have a charge of +3. So if we were to name that, we would say we have, so following our flow chart, is there metal? Yes. Is that metal transition metal? Yes. Count the different elements. We have 2 different elements, iron and oxygen. So that's ionic binary. We're going to name the transition metal first. This guy is called iron. And then in Roman numerals, we're going to give the charge of our transition metal. This transition metal's got a charge of 3. So we're going to call it iron 3. And the next thing you do is change the end. You're going to name the non-metal second. That's oxygen. You're going to change the ending to "ide." So this guy is iron 3 oxide. So going back to our little table, we said this was iron 3. That's iron 3 oxide. We put the iron 3 with the oxide, becomes iron 3 oxide. So one way to figure out how to do your Roman numerals, this is what I just talked you through, but here it is in steps. First thing you're going to do is you're going to add up your total negative charges. What's your total anion charge? You're going to use your anions to help you determine your Roman numerals. Your anions help you determine your Roman numerals. You're going to divide your negative charge by the total number of metal ions. So if your formula says F2, Fe2, you're going to divide by 2, that total charge. And that's going to be the Roman numeral. That's going to be your Roman numeral. Okay, so let's show you what that looks like using the same example again. Our total negative charge for Fe2O3 was 6 because we had 3 oxygens. Each of them was a -2. 3 times 2 is -6. So we're going to divide 6 divided by 2 because we have 2 irons. We have a charge of 3. So this is going to be an iron 3 oxide. Here it is again. You can see it. 2 irons, 3 oxygens, 2, 2, 2. The total negative charge is a -6. Total negative charge is a -6. That means, and so we're going to divide that 6 by the total number of metal ions. We have 2 irons. So we're going to divide 6 by 2. That's a 3, which means each one of these is a +3. Let's double check our work. 3 plus 3 gives you 6. 2 plus 2 plus 2 gives you 6. The charges are balanced. Therefore, this is an iron 3 oxide. Okay. Now, pause the video and see if you can name this guy. Okay, welcome back. So, using your flow chart, is there a metal in the compound? Yes. Is that metal a transition metal? Yes, copper is a transition metal. So it tells you to write down the name of the metal, that's copper, then determine the charge of the uh, anion side. That's nitrogen. Nitrogen always has a charge of -3. So to determine the charge of the copper, you're going to divide -3 with the number of metal atoms you have. You have 1. So your charge for copper is 3. So this becomes copper 3 nitride. Okay, so let's practice a little bit more. So let's name the following compounds. So why don't you pause the video right now and come back once you're done and check your answers. So if you were to look, so welcome back. If you were going to look at A, first question you ask yourself using your flow chart is there a metal? Yes. Is that metal a transition metal? It is. Zinc is a transition metal. However, remember, zinc is one of those ZAC elements that does not behave like a transition metal because it has a fixed charge. So we're going to treat it like a non-transition metal. So we're going to continue going left on the flow chart. Zinc has, so it says count the number of elements. We have 2, 1, 2. So we're going to name the metal first, zinc. And because it does not behave like a transition metal, it has got a fixed charge. You're going to leave it without a Roman numeral. Then it says name the non-metal second. Non-metal is sulfur. Replace the antigen with ide. So it becomes zinc sulfide. Okay, number 2. There is a metal. It is not a transition metal. This is binary. You name the metal first and the non-metal second, changing the ending to ide. Number 3, Cu2Se. Is there a metal? Yes. Is that metal transition metal? Or one of those past elements? Yes. Count the number of elements. 1, 2. We have 2 elements. So what do? We use the anion to determine the charge of the cation. So selenium has a charge of -2. We have 2 metals, so we're going to divide that -2 by 2. That means each copper has a charge of 1. So you name this copper 1 selenide. That's calcium bromide. This is a pass element. We need to find its variable charge. When we do that, we find that it is called tin 2 fluoride. Let me show you how we work out tin 2 fluoride. Here's tin 2 fluoride. It's one of those pass elements. We have 1 tin, we have 2 fluorines. Chlorine has a charge of -1, which means your anion side is -2. We have one metal. -2 divided by 1. That means that tin has a charge of +2. So this becomes tin 2 fluoride. Notice there's no prefixes. That was only for covalent compounds. So I would suggest at this point that you go forward and run through the PowerPoint and go through all the examples. There's a lot more examples for transition elements that I think you should practice with right now. So now that we've learned how to write names for binary ionic compounds, let's write formulas for them. Let's write formulas for them. So again, things that you must remember when you're writing your formulas, going from the name to the formula, is that your compound must be electrically neutral. In other words, your positive charges must equal your negative charges. We have to keep that in mind. Okay, so let's look at a simple one. Calcium chloride. You're given the name calcium chloride. First thing you do is identify that this is an ionic compound. Because it's an ionic compound, you must worry about the charges. You must balance the charges to make sure you have a compound that is electrically neutral. So we know that calcium has a charge. Calcium's right here on your periodic table. It has a charge of +2. We need to know that chlorine has a charge of -1. Our goal is to make, if we put these guys together, is to make something that is electrically neutral. On the left side, on the cation side, we have a charge of +2. That means that this calcium gave away 2 electrons. Where did it give it to? Well, here comes chlorine. Chlorine has a charge of -1. So it gave 1 electron to chlorine, but it still needs to give away another electron. So in order to do that, it has to find another element to give it away to, probably another chlorine. So what you end up having, because this is a binary ionic compound, what you end up having is one calcium and 2 chlorines. You have a +2 on the positive side and a -2, -1 plus a -1 is a -2, and a -2 on the anion side. That is electrically neutral. So your formula is Ca, 1 calcium, and 2 chlorines. That is your formula. Notice that there is no charges within the formula. Overall, the compound is electrically neutral. There is no charge. Calcium's got a charge and chlorine has a charge, but when you put them together, you have an electrically neutral compound. So when you are trying to write formulas for your binary ionic compounds, what you're going to do is you're going to write the ions and their charges in the compound, and you're going to determine how many of each ion are needed to make a neutral compound. You're going to list the cation symbol, then the anion symbol. You're going to add the subscript, that's down at the bottom to indicate how many of each ion is in the formula, to give you the lowest whole number ratio. If you only have one of an element, you do not have to write the subscript 1. It is understood. You do not write it. For instance, CaCl2. We don't write Ca1Cl2. We wrote CaCl2. Okay, let's do this for aluminum fluoride. First thing you do is identify that this is an ionic compound. Because it's an ionic compound, we worry about charges. We look at aluminum. Aluminum on the periodic table has a charge of +3. Fluoride on the periodic table has a charge of -1. So you write those guys down. This side has a +3. This side has a -1. We need them to balance each other out. So we need to add 3 fluorines. So you have a -3 on this side and a +3 on that side. So our formula is AlF123. AlF3. Remember, you never include the charges, positive or negative, in the actual chemical formula of a compound. Okay, so why don't you practice writing some of these? I'll pause the video and we'll come back in a minute. Okay, welcome back. So, strontium phosphide. So the cation you have is strontium, which is Sr. That has a charge of +2. Phosphorus is P3 minus. That is phosphorus, which has a charge of 3 minus. So you have an S3, P2. In order to make them electrically neutral, you end up with a formula of S3, P2. For potassium sulfide, potassium has a charge of +1. Sulfur has a charge of -2. You need 2 potassiums so you can make your charges equal. You get a K2S. Iron 2 oxide. Iron has a charge of +2. Oxygen has a charge of -2. This iron has a charge of +2 because of this 2 in parentheses, the Roman numeral. That's the charge of iron. So you have an iron with a +2, an oxygen with a -2. They are already balanced, so you have 1 iron and 1 oxygen. Okay. There is a shortcut for this, and that's called the crisscross method. Okay? The crisscross method is an easy way to figure out the formula for an ionic compound. This only works for ionic compounds, and that's to swap the charge of each ion and use them as subscripts. But we do this with the absolute value of the charge. In other words, we're swapping the number, not the charge. Just the number, not the charge. And the formula must be in the smallest whole number ratio. So let me show you what that looks like. Sodium has a charge of +1. Sulfur has a charge of -2. What you're going to do, you're going to take those two numbers. The 2 is going to go over there, and the 1 is going to go over there. It is the absolute value of those numbers. Notice that the charges aren't circled, just the numbers. You're going to crisscross them. So there goes the 2. There goes the 1, but we don't need to write the 1. We drop the charges. You get an Na2S. Na2S. Okay, now let's try for the aluminum fluoride one. This is one we had before. We balanced the charges. We said, oh, we have a -3. We have a +3. We're good. We said our formula was AlF3. But if we do the crisscross method, we know aluminum has a charge of 3+. Fluorine has a charge of -. We're going to crisscross. That number goes there. It's a 1. We don't really put anything. That goes to 3. And you end up with this number goes there. That goes there. And you get the same charge. Okay. Let's do it for iron 3 bromide. Iron 3 has a charge of +3 because iron is 3. Bromine has a charge of -1. We're going to crisscross. This is a 1. When you just put a minus, that's the same thing as saying a 1. We're going to crisscross the 1 there, the 3 there, and we're going to drop the charges. There goes the 3. There goes 1. FeBr3. Okay. Now, if your charges are equal, then you don't need the crisscross method. Just show one of each, 1 ion of each. If you do Mg2+ and S2-, you're already balanced. You don't need a crisscross. You already know you're balanced. You have 1 magnesium, 1 sulfur. But if you were to balance, if you were to crisscross, you would have to remember to reduce to the lowest whole number ratio. If you were to crisscross, this would become an Mg2 and an S2, and then you would have to reduce it down to Mgs. Smallest whole number ratio. So I'm going to show you what I mean by that in the next formula. If you were trying to put together the formula for lead for sulfide, lead 4 means it has a +4 charge. Sulfur has a charge of -2. Let's crisscross that. 2 goes there, 4 goes there. We're going to crisscross them, drop the charges, and we end up with a formula that's Pb2S4. However, that is not the lowest whole number ratio, so we need to reduce that. There we go. Now, if you were to balance your charges like this, you would say, well, Pb's got a 4+, sulfur's got a 2-, so we're going to need 2 of those. Now we're balanced, and we get the same formula. So why don't you practice doing the crisscross method for the following, which were the same problems we did before, but try using the crisscross method for these. I'll pause it while you do that. Okay, welcome back. So you should have gotten, as you already know, SR3P2. Strontium was a +2. Phosphorus was a 3-. So you get a S3P2. Potassium sulfide is a K2S. And iron 2 oxide is an FeO. Okay, now let's try these three. Okay, I'm going to pause the video and then come back for the answers. Okay, antimony has a charge of +5. Nitride has a charge of -3. When you crisscross that, you end up with an antimony that has a 3 because we're crisscrossing the 3 from nitrogen, and a nitrogen that's got a 5 that came from antimony, Sb3 and 5. Iron 3 chloride, you have an iron with a 3 plus, a chlorine with a minus. You're going to crisscross it. That means the minus from chloride goes to iron. So you have one iron. The 1 from chloride goes to iron. You have one iron. And the 3 from iron goes to chloride. So you have 3 chlorines, FeCl3. Calcium has a +2. Bromine has a -1. You crisscross, you get a CaBr2. So now let's write formulas for ionic compounds that have polyatomic ions. We haven't done that yet, and then we're going to learn how to name things with polyatomics. So when you're writing formulas for polyatomic compounds, we're going to write it the same old way that we did the regular ionic compounds, except for we're going to need to use parentheses to keep those polyatomic ions together because they act as a whole unit. So we want to kind of like lasso them together, glue them together so we don't separate them. You're never going to change the formula of a polyatomic ion. If you read the polyatomic ion as CO3, then you keep it as a CO3. Put a parenthesis around it to keep it together. So what does that look like? So this is your list of polyatomics, or a list of some of the polyatomics. If you'll notice, most of them end in 8 or an ite. If you see something that ends in an 8 or an ite, that right there is an indication to you that it is a polyatomic. There are a few of them that end in IDE that you need to know. For instance, cyanide and hydroxide that we use a lot. And here's your one positive polyatomic, ammonium. Anyways, what I'm about to say applies for all of them. If you were to select a polyatomic at random out of this list, let's select chromate. CrO42 minus. This is what it looks like. What I want you to get in the habit of doing is putting parentheses around everything except for the charge. The charge is the thing in the top right-hand corner. I want you to put parentheses around everything and have the charge be on the outside. When you do that, that reminds you that this is one unit. And this charge belongs to this unit. It doesn't belong to the oxygen. It doesn't belong to the chromium. It belongs to the unit, to CrO4. So put the parenthesis around the polyatomic and leave the charge on the outside of the parenthesis. Remember, the charge is the thing that's up on the top right-hand corner, not the thing on the bottom. Okay? So let's try putting a formula for this. Again, we're going to identify these as covalent or ionic. Polyatomics tend to be with ionic, but let's identify the way we've identified everything else. Is this an ionic or covalent compound? Well, it's got a metal, therefore it's got a cation, it is ionic. So if we were to write down the formula for this, we know we worry about the charges. Well, we know that calcium has a +2 charge. You see something that says nitrate, it ends in ATE. That's an indication to you that that this is a polyatomic and you need to go look it up. And you find it in the polyatomic sheet as NO3. You'll see it as saying it says NO3 like that. You put the parentheses around the NO3 and you leave the charge, the thing in the top right-hand corner, off by itself. So now we're treating it as one unit. We're going to put this together like we did every other compound up till now, every other ionic compound up till now. We can do one of two things. We can balance the charges. Or we can do the crisscross. So we're going to do both ways, just depending on what you prefer. You have a +2 over here. You have a -1 over here. So we're going to add another nitrate, and that gives you another -1. So now we have a -2, and we have a +2, which means we have calcium, 1 calcium and 2 nitrates. We're keeping that nitrate within that parenthesis, and that 2 goes on the outside. That's saying we have 2 of these units, because we have 2 of them. Look, 1, 2. We don't distribute that 2 in here. We don't say we have 2 nitrogens and 6 oxygens. We keep it on the outside. Now, if you were to crisscross that, this is what it would look like. You have a calcium, the 2 plus, and you have a nitrate with the -1. Just put those parentheses in there. That 2 is going to go there. The 1's going to go there. And you end up with a CaNO3, 2. Same formula. See? Same formula. Let's do a couple more practice problems. Let's do strontium sulfate. Strontium has a charge of +2. Sulfate has a charge of -2. Let's put those parentheses in there. So now we see that our charges are already balanced. We don't need to crisscross. We already see our charges are balanced, which means that we need only 1 strontium and 1 sulfate. This is what it looks like. Now, because we only have 1 sulfate, we don't have to put the parentheses around the sulfate. However, I think it's a good habit to get into because it draws your eyes to it. But either one of these answers are correct. I tend to do it with the parentheses because it draws your eye to the polyatomic. Let's try lithium carbonate. Lithium has a charge of +1. Carbonate, ends in ATE. Let's go look it up on the polyatomic list. We see that it is CO3 2-. Make sure that we put those parentheses in. We can either balance our charges. We have a -2 here, so we want to add another lithium here. So we get 2 lithiums, 1 carbonate, or we can crisscross. Either way, we get the same formula. Again, we don't need those parentheses. However, it is not wrong if you keep them here. I would probably keep them. Okay, let's try another one. Let's try magnesium hydroxide. Magnesium has a charge of +2. Remember, I told you hydroxide is one of those polyatomics that ends in IDE. You need to know it because we use hydroxide a lot, especially when we get to the acid-base unit. Hydroxide is an OH-. It is a polyatomic. Put those parentheses in. We're going to balance our charges. We have a +2 here. We have a -1 here. So we're going to need another one. Now we have a -2 on this side and a +2 there. So this is 1 magnesium, 2 hydroxides. 1 magnesium, 2 of these hydroxides. We're not breaking those hydroxides apart. That means we have 2 of these. We want the 2 on the outside of that parenthesis. Or you can crisscross. Here, it is necessary for you to have that parenthesis for hydroxide because we have 2 of them. If we only had 1, then you don't need it. But if you have 2, it is necessary for you to have it. Okay, one last one. Let's try ammonium dichromate. Remember, ammonium is your 1 positive polyatomic, your 1 polyatomic cation. So if this is a cation and this is an anion, you have an ionic compound. Doesn't matter that they're 2 polyatomics, we still treat them the same. We're going to treat our 2 polyatomics as 1 unit each. So you have ammonium, which has a charge of +1. You get that right off the polyatomic list. Dichromate, you look off the polyatomic list also. It's Cr2O7. Put those parentheses around them. We need to balance our charges. We have a -2 here, so we're going to need 2 of these. 2 of these, 1 of those. Or you can crisscross. Again, treating it as a unit. Let's get those parentheses in there. This 1 goes here. That 2 goes there. So you end up with NH42, Cr2O7. Okay, why don't you practice these? And pause the video, try them, and then come back. Okay, welcome back. Strontium sulfate. You get SrSO4, or you can write it as SrSO4. Strontium has a charge of +2. Sulfate has a charge of -2, so they're already balanced. Lithium carbonate, Li2CO3 or Li2CO3. Either one works. Lithium has a charge of +1. Carbonate has a charge of -2, and you get that formula. Potassium sulfate. Potassium has a charge of +1. Sulfate, SO4, has a charge of a -2. You put those together, you get K2SO4, or you can write it with the parentheses. Either one works. And magnesium hydroxide is the one we just did. That's a practice problem, but you get MgOH2. One more set of practice for you to go through. Ammonium dichromate. That's the one we did earlier. Potassium permanganate, sodium hypochlorite, and barium sulfite. Pause the video, and when you come back, you'll see the answers displayed. Okay, here are your answers. Ammonium dichromate. We did that one earlier. Potassium permanganate. Permanganate has a charge of -1. Potassium has a charge of +1. So you get KMnO4. Sodium hypochlorite. Sodium is a +1. ClO is a -1. So you get this formula. Remember, ite and ate means polyatomic. Barium sulfite. Barium's got a charge of +2. Sulfite's got a charge of -2. Those charges already balanced, so you need one of each. And that's it. Okay, the last thing we're going to talk about in this unit is now naming ionic compounds that contain polyatomics. So we just talked about writing the formulas, but now we got to talk about naming. And this is pretty easy if you can do the rest of the naming. So now we're going to look at our flow chart, one of the parts we haven't done yet. We said, is there a metal in the compound? Yes. Is that metal a transition metal? We're going to start with no. We're going to count the different number of elements. If there are 3 or more elements, then you are ionic ternary, and all you're going to do is name the metal first, and then name the polyatomic ion second. You're not making any changes. Name of the cation, then name of the polyatomic. Okay. If there are more than 2 elements present, then you have a polyatomic ion present somewhere. And only one polyatomic is cation, that's NH4. All the other ones are anions. And you're going to name it just the way we do ionic compounds without changing the ending. Remember, ate and ite indicate polyatomic. So, ZnSO4. This guy is zinc. It's one of those it's a transition element, but it has a fixed charge, so we don't need to give its charge in a Roman numeral. So that guy is just zinc, so we're naming the metal first. Then what's this guy called? You look him up on your polyatomic sheet and you see it's sulfate. His name is, it's right here, sulfate, SO4 2-. SO4 is right here. So this guy's name is zinc sulfate. What about NaOH? If you follow your polyatomic chart, it says, is there a metal? Yes. Is that metal a transition metal? No. Count the number of elements. Sodium, oxygen, hydrogen. 3 elements. So that is ionic ternary. We're going to name the metal first, sodium. Then we're going to name the polyatomic second. OH is right here, hydroxide. Sodium hydroxide. Okay, let's try these. Name these compounds. Is there a metal? Yes. Is that metal a transition metal? No. Name the metal first, calcium. Name the polyatomic second, carbonate. Calcium carbonate. You look this guy up in the polyatomic sheet, it is carbonate. Is there a metal? Yes. Is that metal a transition element? No. Name the metal first, name the polyatomic second. Name the metal first, name the polyatomic second. Okay, same here. Name the metal first, name the polyatomic second. This guy is called tin 2-phosphate, and we're going to go through that one in a minute. And this one is sodium chromate. You should try those out. We're going to do tin 2-phosphate right now. SN3PO4 2-. Okay, like we did for all of our other things that had transition metals, we're going to treat this the same way because phosphate is just an anion. It looks bigger, but it's still treated as one unit. So we're going to go through our flow chart. Is it a metal? Yes. Is it a transition metal or is it a pass element? SN is one of those pass elements, those 4 that are non-transition metals that behave like transition metals. So we treat it like a transition metal. So we need to determine the charge for SN in this case. So how are we going to do that? The same way we did all the other ones. We're going to use the anion to help us determine the charge. We know that we have 3 tins. 1, 2, 3. We have 2 phosphates. 1, 2. We know the charge of phosphate is a -3. We have 2 of them. So our anion side is -6. We have 3 metals. So -6, or 6 divided by 3, gives you a +2 for each of those. 2 plus 2 plus 2 gives you 6. 3 plus 3 gives you 6. We're balanced. So the name of this guy is going to be tin 2, because he's tin 2, and then phosphate. Tin 2 phosphate. So that on the flow chart looks like this. Is there a metal in the compound? Yes. Is that metal a transition metal? We're treating, is it a transition metal? And you should say, or a pass element. Yes. Count the different number of elements. If there are 3 or more elements, we're ionic ternary. You're going to name the transition metal first. You're going to determine its charge from the anion, and then you're going to name the polyatomic second. And that's all we have for ionic compounds. Next up will be acids.